Hello guys, in this lecture we are going to talk about graphs of functions. So if f is a function with domain z, like z describes all axes which you can plug into the function, then the graph of f is a set of ordered pairs where x and f of x are working as x and y, and I think I'm missing one parenthesis over here, and x belongs to domain. So it's like you kind of put all x's possible and calculate all f of x's, make up pairs of x and f of x, which are going to be working as x and y, and graph all this as points on coordinate plane. Okay. Yeah, I think what I'm going to do, I'm going to edit a little bit this. I don't like that, but we have it without parentheses. Let me put kind of more parentheses. Good. Okay, and let me erase this one, which I don't like. Okay, so that's definition of a graph. Shift it a little bit. My definition of belonging symbol is not going to work. Okay, perfect. Now, what I'm going to do, I'm going to talk about some important graphs we will need to know. So I'm going to write down important graphs. So what important graphs we'll need to know? We're going to start with a very simple function. F of x equals a constant. Constant means that can be kind of number, but it's not changing because of x. I'm choosing constant f of x equals 5. Can be any number, maybe -1, 0. But you see there is no x here. So for all x's, it's the same number. Well, what kind of pairs of numbers we can have? Well, we can have pairs of numbers 5 for x, for example, and 5 for y, right? You plug in x equals 5 and nothing changes. We also can have 0 for x and 5 for y. We also can -1 for x and 5 for y. Basically, for all possible x's, it's going to be just one same value. I'm going to graph it as a straight line. This straight line is going to go through the point 5 on y-axis, and it's going to have the same value for all axes. So like x equals 1, it's 5, x equals 2 is 5, x equals 3, 4, 5, it's still 5 over here. My axis on y, my y-axis scale is a little bit different from x-axis scale, but kind of, that's me who is defining this. So my 1 here on y-axis is much smaller. Okay, that's called a constant function, and it looks usually like a horizontal line. Okay. Next function is going to be a little bit more complicated, and that's going to be a linear function, 2x. 2x, here x changes and changes f of x. Well, how it's going to look? Well, I'm going to calculate few values and then do the graph, okay? I'm going to draw a table. Here going to be x, and here is going to be f of x. So x equals -1, -1 by 2 is -2. X equals 0, 0 by 2 is 0. X equals 1, 1 by 2 is 2, and x equals 2, 2 by 2 is 4. Now what I'm going to do, guys, well, I do actually know how the graph is going to look. So I'm going to graph this 4 points and then kind of continue the graph. So -1 equals at x equals -1, y equals -2, somewhere here. 0 is 0, 1 is 2, well, and 2 is 4. Well, actually 4 is not gonna fit over here. my scale is too short. I think 4 is supposed to be somewhere here. I'm going to draw it in red line. So my graph is going to look like a straight line, actually. Well, I do know it's a straight line. Otherwise, I should use a graphing calculator and just check every point on this graph. It's going to be a straight line. Okay, straight line which goes through the origin. And let me label on my graph 1 and origin. And here is going to be y, and I labeled x already. This is called linear function. And if you don't add anything over here, it's going to always go through x, through the origin. Next one, function number 3. f of x equals x squared, squaring function. Again, I'm going to start with a table and then do the graph. So I'm going to put here x and here is f of x. You can also put y here. I'm going to do -2, -1, 0, 1, and 2. So -2 square, 4, -1 square, 1, 0 square, 0, 1 square, 1, and 2 square, 4. Now I'm ready to graph. Guys, I'm going to be a little bit more careful with like my units here. So I want my graph to fit actually here. So I'm going to label 1 over here, 2, 3, 4, and also 1, 2, 3, 4. Y-axis, x-axis, origin, right? -1, -2, -3, -4. I'm going to do just only -1. Now I'm going to use a red color to graph it. So at -2, which is over here, it's 4. At -1, it's 1, somewhere here, 0 is 0, and at 1 is again 1, and at 2, it's going to be 4. Well, what we are going to have is a parabola. I think everyone knows what is parabola. It's just like, you know, the first time you can graph it by points, but then you just can graph something like this. And that's going to be a function x squared, okay? Our next function is going to be x cubed, a little bit more complicated. Number 4, f of x equals x cubed. I'm going to do a similar table over here. So guys, I'm not going to do -2, okay? I'm going to do just like -1, 1, and 0, okay? -1, 0, and 1. Why I'm doing this, because actually if I cube 2, it's going to give me, maybe I should do this actually. It's not that bad. Let's do it. Yay. Well, we're just going to do a different scale on y-axis. So I'm going to do here -2, -1, 0, 1, and 2. -2 cubed is going to give me -8. -1 cubed is going to give me, oh, sorry. It's going to give me -1. 0 cubed is 0, 1 cubed is 1, and 2 cubed, 3 times 2 is 8. Now I'm going to graph it here because my function is kind of getting large values. I'm going to do bigger scale on x-axis, so it's 1 and 2 here. -1 and -2, and a smaller unit on y-axis. On y-axis, I'm going to do like over here, like 4, and over here is going to be 8. Yeah, because numbers are bigger and my graph is going to be very big. Now I'm just going to start graphing my points, okay? So my first point is -2 and -8. -8 is somewhere here, -2 is here, so -2, -8. The second point is -1 and -1, -1, -1. -1 is going to be somewhere here. If this is 4, -1 is somewhere here, very close to x-axis. And then 0 is going to give me 0, 0, 0, 1, 1. Well, somewhere here, right? Because if it's 4, 1 is 1/4 of my scale. And 2 is going to be 8, somewhere here. Now I'm going to connect these points in a small line. And what we have is a cubic parabola. What I think my actually cube doesn't look like a cube over here. I'm going to write it down better, like 3. Okay, cubic parabola. Function number 5. Function number 5 is going to be a square root function. F of x equals a square root of x. Again, I'm going to start with a table, and I'm going to put x here and f of x over here. Well, guys, for square root, we do know that we cannot put negative numbers under the square root. So I'm going to start with zeros and do 1. I know that I don't want to extract a square root of like 2 because it's going to give me a square root of 2. So I'm going to extract a square root of 4, and my next one is going to be 9. So it's going to be 4 values. Square root of 0 is 0, right? Square root of 1 is 1. Square root of 4 is 2. And square root of 9 is 3, right? And we even don't need this part. Now I'm going to graph it. Let me draw plane. Here is going to be x, and here is going to be y. Now, guys, because my axes go from 0 to 9, maybe I'm going to do 2 here, 4 here, 8 here, right? No, 2, 4, no, it's supposed to be 6, sorry. 8 is too early. 6 and 8 here, and maybe 10 here. And over here, I'm just going to do 1, 2, and 3. So I'm going to start with point 0, 0, 0, and then 1, 1. Well, my 1 is somewhere here, so 1, 1 is here. My point 4, 4 is going to result into number 2, and my point 9, which sits somewhere here between 8 and 10, somewhere here is going to be 9, is going to result into number 3. And that's going to be my square root function. Okay. And the last function I'm going to describe, it's not like there are only 6 functions possible, but there are basic functions. The last function I'm going to describe is inverse function, which is going to be 1 over x. Again, I'm going to do the table. I'm thinking like if I want to do, like, okay, I'm going to do -2, -1, 0, 1, 1, and 2. Okay, that's okay. I'm going to substitute first -2. -2 here is going to give me -1/2, right? -1 is going to give me -1. Can I substitute 0 here? No, I cannot substitute. I'm going to put undefined. Undefined means that if I plug in 0 here, I'll need to divide by 0, which I don't know what is going to result. So undefined. Now I'm going to substitute 1 here, and 1 over 1 is 1, and 1 over 2 is 1/2. Now I'm just going to use these points to build my graph. Guys, graph is called hyperbola. Okay. Well, that's going to be 1, that's going to be 1, that's going to be x, and that's going to be y. So let's start with -2 and -1/2. -2 on x-axis is over here, right? -2, and -1/2 is going to be over here. Then we are going to have -1, and that's going to be -1 over here. Next, we are going to move over here, and we are going to find that 1 is 1 at 1, 1, right? And 2 is 1/2. 2, which is over here, is 1/2. Now, guys, I do know how the graph is going to look, so you will need to trust me in this case. But actually, we are not just connecting the points. We're going to connect them like this. Why? Well, later I'm going to explain how to find it out. But for now, guys, let's think what is going to happen when x is becoming closer to 0. We know that at 0 it's undefined, but when it's becoming closer to 0. For example, if you set up x equals 0.001, what is going to be the value here? F of 0.001 is 1 over 0.001, which is going to be what? 1,000, right? 1,000 is a huge number. So we're getting closer to 0, and my function moves to positive infinity, actually getting bigger, bigger, and bigger. And if you're getting closer to 0 on this side, everything is same, just as going to be the minus in front of x, which is going to give you a negative number, and that will go to negative infinity. Okay, the function is called hyperbola, and we are going to deal with it a little bit later in like more details. But for right now, you just need to know how it looks. Okay. One more, or let's say one more type of essential functions is called piecewise defined functions. Sorry, guys, the wrong. What are piecewise defined functions? Sometimes function f has different formulas. Remember, what are formulas? Formulas is something like this or something like this. Sometimes f of x has different formulas on different intervals. That happens sometimes. You decide that, for example, I'll give you an example. I'm going to write down f of x has different formulas on different intervals. What can happen? Well, if you set up f of x equals, for example, a square root of x when x is greater or equal than 0, and 1 over x when x is less than 0, means that it's going to be a different graph on different interval. I'm going to try to graph this piecewise defined function, and there are many of them, and we are just going to graph one as an example. So a square root of x when x is greater than 0. Where is x greater than 0? X greater than 0 over here. It's supposed to be square root of x. Let's scroll up and see how square root of x looks. Looks like this, okay? So I'm going to graph where x is greater than 0. My function is going to look like this. I'm going to label over here 1 and 1. What happens when x is less than 0? Over here, negative axis. It's 1 over x. 1 over x looks like this, hyperbola. And it can happen in life too. So actually, this is typical piecewise defined function. Different pictures on different intervals and different formulas. Very important example of piecewise defined function is absolute value. I'm going to set the function f of x equals x when x is greater or equal than 0, and negative x when x is less than 0. Graph it, and then maybe we kind of label it. So how this graph is going to look? Well, it equals to x when x is greater than 0. X is greater than 0 over here, and like you plug it x and you get x as a result. For example, you plug it 1 and you get 1 as a result. Plug 2, get 2 as a result. So it's going to be a straight line going like this. If you are on negative side, for example, negative 1, then function tells you if you have a negative x less than 0, then you need to use as y value minus this x, so which is going to be minus negative 1, for example, which is going to be positive 1 over here. Same is going to happen to negative 2. If you have negative 2, it's going to be minus negative 2 or positive 2. And the graph is going to look like this. Well, my straight line doesn't look like straight. I'm going to do it one more time more straight. Okay, so actually this function has a special name. This function f of x is called absolute value of x. And that's how we define it as a formula. And that's how it looks. It looks like a right angle actually, right? Okay, very good. Now guys, let's talk a little bit about like graphs and how we can find out whether the function or the graph represents a function or no. So vertical line test. Is graph a function or no? Okay, so what do I mean? I'm going to draw two functions or two graphs, let's say, and then we are going to investigate whether they can be functions or no. Okay, my graph number 1, which is not number 1, but A, and my graph number 2, my graph B. Two graphs, and I'm going to investigate whether they are functions or not functions. Remember, the only condition for relation to be a function is for every x supposed to be only one y existing, right? Well, what we can do actually, guys, we can draw a vertical line. My vertical line, definitely not vertical exactly, vertical line, and start moving or sweeping this vertical line along axis and check how many times it intersects the graph. If it intersects only once, then for this particular x, there is only one y, right? And if we move the line over here, I'm trying to make it more vertical. For this particular x also, only one y. So you see that this relation is a function because for every x here, we're going to have only one y. What is going to happen here? Well, I'm not going to investigate what happens here. I'm going to investigate interesting area over here. If I choose x over here, how many different y's I'm going to have? Well, look how many times it intersects my graph. It's y1, y2, and y3. So 3 different y's. And we are going to have a situation when 1x goes into 3 different y's, y1, y2, and y3. We remember that if it's a function, then we cannot have like 3 different y's. So we can say that this graph is not a function. A function. Visually, we can use so-called vertical line test. If you draw a vertical line test on your graph and kind of imagine that you are moving it from negative axis to positive axis, and your line crosses your graph exactly once everywhere, then it's a function. If it crosses more than one, sometimes like 2 times or 3 times, then it's not a function because it breaks the definition of a function to have only one y for every x. It does not matter that it breaks definition only in one region. If it does not break it here, but breaks it over here, it's still not a function unless you kind of remove this region totally. Okay, we call it vertical line test. I'm going to give you a couple of examples of real functions. These were fake functions, but real functions. One is going to be a function, one is not going to be a function. So example number 1, I'm going to draw a circle. And circle is something like this, right? I'm going to write down the equation of this circle. We still remember that x squared plus y squared equals radius square. Radius here is 2, so it's going to be 4. Is it a function, this graph? Well, let's draw a vertical line. You see, vertical line here intersects my graph in 2 points. So we are going to write down that it's not a function, not a function. Okay, one more. I'm going to just maybe consider example here. Example 2. Well, guys, we did not cover yet trigonometric functions, but you probably kind of seen something like this, a function which looks like this. Function is called a sine of x function. And if we check this function, this graph using vertical line, we're going to see that it intersects vertical line exactly once, which means that that's going to be a function. Okay, now the last thing I want to talk is increasing and decreasing of a function on interval. So let me scroll a little bit. Guys, I'm going to set up a definition. Definition. F of x is increasing on interval. I'm going to label it I, interval I. I can be like interval from A to B or from negative infinity to positive infinity. So that's why I label it I. If for any x1 less than x2 from the main follows that f of x1 is going to be less than f of x2. F of x is decreasing on interval I if for x1 less than x2, any x1 less than 2 from domain D follows that f of x1 is greater than f of x2. I'm going to give you kind of example of increasing. Imagine that the function is looking like this. So let's pick up x1 and x2, and they're supposed to follow certain inequality. X1 is supposed to be to the left of x2. And let's check what is going to happen to the values. This is y1 and this is y2. You see that y2 is greater than y1. So that's increasing function. Graphically, increasing function means that when you move in positive direction of x-axis, when somebody is moving in positive direction of x-axis from the left to the right, he's climbing up. So somebody is moving up, means increasing. Now decreasing. Oh, sorry, I want to use black one. Give me a second. Function is decreasing. If somebody moves down, I'm going to show you an example of decreasing function. Well, something like this. It's a straight line. X here, Y here. And you pick up X1 and X2. And you see that obviously that Y1 is greater than Y2. Greater because kind of going to be above. For decreasing function, if you imagine somebody walking in positive direction of x-axis from the left to the right, he goes down. So decreasing function goes down and the increasing function goes up. Let me give you an example which kind of combines both increasing and decreasing intervals. Example, f of x equals x squared. I'm going to graph the function and then talk about intervals. Well, we already know how the graph is going to look. Remember, that was one of important functions we had in like previous 10 minutes of the class. That's how the function looks, right? I'm going to label 1, y, and x. If we consider somebody walking, we see that this walking person from negative infinity up to the point 0 is going to go down, right? So we are going to write down the decreasing from negative infinity to 0. And if you imagine after 0, somebody walks over here, he goes up, increasing from 0 to positive infinity. So one function has intervals where function is increasing and function is decreasing. That's normal for a function. It can have many intervals, increase or decrease at the same time. Or sometimes it's going to be always increasing or always decreasing. Like in my examples, for example, this example of exponential function, it's always increasing, right? And this is example of linear function, it's always decreasing. But the quadratic function is doing both. Okay, now I'm going to put some self problems and I kind of expect you to solve them. Well, there are going to be just 3 of them. Problem 1, graph f of x equals 1 minus x to the power of 4. Problem 2, f of x, also graph for both problems, equals 1 when x is less or equals than 2 when x is sorry, wanted to do double inequality on 2, 4, and 3 doesn't look like 3 actually, 3, 4, x is greater than 4. Okay, and the last problem is asking if the graph below a function is it a function. I'm going to graph ellipse, and well, again, formula is not very important. I just want you to judge by the like look of the graph. That's my graph, and the question is it a function? Okay, and as you kind of remember, I'm going to count to 5, but you can stop my video and try to solve this problem on your own. So I'll start counting 1, 2, 3, 4, 5. And let me start solutions. So for the first graph, guys, there is only one way to graph for us. Either use graphing calculator or you do the table. I'm going to do the table for the first problem. I'm not going to graph too many points. I'm just going to do like 3 points, okay? So my points are going to be -1, 0, and 1. Okay, just 3 points, and I'll try to use them to do the whole graph. So -1 to the power of 4 is going to give me 1. 1 minus 1 is 0. 0. 1 minus 0 is 1, and 1. 1 to the power of 4 is 1. 1 minus 1 is 0 again. Well, it looks a little bit strange, but because I do know how the graph is going to look, it's not going to be a problem for me. I'm going to be my x, and there's going to be my y. So I'm going to graph these 3 points. Sorry, That's 1 here and 1 here. So at -1 and 1, the graph is equal to 0. And at 0 is 1. So these are my points. I'm going to connect them. Actually, guys, what I'm going to have is going to be another parabola. And this parabola is going to go down, the branches down, and you can always do more points if you wish. Or you can use your graphing calculator and just look how the graph looks. Okay. Solution of problem 2. Well, here is piecewise defined function, and it has several intervals. I'm going to do number line first, or like coordinate plane actually. And on this coordinate plane, mark the intervals. So I have my interval from negative infinity to 2. Let's imagine that 2 is over here. Then from 2 to 4, 4 over here. Or maybe I should do like more separate points. Let's do 1 here, 2 here, 3, 4, 5, because I don't have anything more, right? And 1, 2, 2, and 3 over here, and there is y. Okay, so from negative infinity to 2 is going to be equal to 1. So it's kind of a constant line equals to 1. And I'm going to make a dot over here because actually at 2 exactly it equals to 1. Now starting 2 up to 4 is going to be equal to 2. So I'm going to graph it like this. It's still constant line. If you look over here, you see that at x equals 2, it's not equal to 2. It's actually at x equals 2, it equals to 1. So I'm going to put a hole over here showing that when x equals 2, the function equals 1, not 2. And here I'm going to put a dark circle because at x equals 4, the function equals 2. The last interval is from 4 to infinity, and the function is equal to 3, the constant. 3 is over here, right? Y equals 3. And again, I'm going to put a hole over here because actually when x equals 4, it's not 3. When x equals 4, it equals to 2, belongs to this interval. And that's my function. Looks a little bit crazy, but still, why not? And the last example, I'm just going to solve it right on my picture. So I'm going to draw a vertical line and see that my vertical line intersects my graph twice, right? So two different y's, y1 and y2. So y1 and y2 for 1x. Not a function, right? Not a function. Function or the graph does not pass vertical line test. Okay, that's all. Well, do your homework and I'll see you next lecture. Okay.